So again, it's a pleasure. I see so many new faces and young people. And I'm a professor at Georgia Tech. I work on autonomy for drones and security. And I have been at Georgia Tech for about 8 years. I was at Virginia Tech before. And we have been working on many cool projects. So again, I'm a control theorist, so I will have some basic equations, but don't worry too much if you don't understand them. You can always find me after. Okay. So again, my lab is called Intelligent Cyber-Physical Systems, and one cyber-physical system is also the drone. Okay, so every system we can model it as a cyber-physical system, and I will explain what it is. So it's just some cool figures, but the government recently announced that cyber-physical systems are very important because our lives depend on them. Again, remember that we will model a drone as a cyber-physical system. But of course, we have to consider, actually, from the previous talks, we have to consider security, autonomy, and how they both can interplay between each other, and how we can make them work without any pre-training. Okay, so again, learn on the fly while you're protecting your sensor and actuators. And then I will talk about some open research ideas that we're working or we're not working, and I will be happy to talk to you and work with you. Okay, so what is the motivation and why we want to work on this topic? And again, in the broad area of cyber-physical systems. So what is cyber-physical system? Again, I mean, this is two words, cyber and physical. So it means integration of computational algorithms and physical components. And they have been all over, from process control networks, manufacturing, energy, aerospace, automotive, power systems, so on and so forth. Okay, so one very important topic, I think, one of the previous speakers also mentioned, is how you can guarantee security, especially when you have very critical missions, such as the ones that are being dealt with drones. So there are two different topics here. So I'm sure some of you are familiar with cybersecurity, some of you are familiar with fault detection. So what we work as control theorists, we work on something that we call cyber-physical security. And why? Because this exploits also system dynamics. What I mean by system dynamics, I mean the physics of the system. Okay, and of course this assesses correctness of the measurements, so what your sensors are measuring and how these sensors can actually move your actuators and then move your vehicle around. So of course, this is some differentiation between classical fault detection and adaptive control, where they consider general failures. For us, we consider worst case attacks. And of course, cybersecurity, from the pure software side, does not exploit compatibility of measurement with physics or dynamics. So of course, as controls people that we work on these topics, we try to bring ideas together from different things, and you will see actually what I mean by that. Okay, so cyber-physical systems, of course, they get smarter and smarter. I know AI is big right now. I mean, it has been for many years, but now it's getting bigger and bigger. So the time that you incorporate more intelligence into your systems, then this opens more doors for for the attackers to attack. Okay, so let's see what we can do. So we have developed some frameworks over the years. So there are two types of frameworks for security. One is proactive security and one is reactive security. So proactive security is the one that you want to confuse the attacker of what you use with respect to your sensor and actuators, because these are the most important things of your drone or any system, and you want to confuse them, and then you want to increase your attacker surface. Okay, so the attacker doesn't know what currently you're using in terms of sensor and actuators, and then it doesn't know where to attack. Okay, and this has been around in many areas. So of course, people in network security have been working on that. People in IT-centric approaches have been working on that. But in the control side, for example, when you control your system, there's not any work. So we have tried to do that, and we have to bring this idea of proactive security. So also people, they call it moving target defense, because you are changing things in your system to confuse the attacker. So you will see how we can eventually do that in a drone system or aircraft system or anything we can think. Okay, so this is my motivation here. And again, as I said, a constantly changing system makes it harder for the attacker to find the best attack strategy, okay? So again, you can think, if I don't know what sensor and actuators you're currently using, then I don't know what to attack, okay? Or I attack something that is not important for you. Okay, so actually the idea is pretty simple. So you have, wherever you see the plant here, you can put any system. For example, you can put a drone, you can put an aircraft, and so on and so forth. And we have two systems that are working together. One is the proactive security, where I confuse the attacker, and the reactive security, let's say that the attacker was lucky enough and found what sensor and actuators we're using. So then we have an intrusion detection, which is model-free. We detect the sensor and actuators, we isolate them, and then we take them out of the switching queue where we use it in the moving target. Again, you can think that we can have sensor and actuator attacks. Again, sensors are the things we can measure, and actuators are the things we can move, okay? So we consider attackers that they enter into the control or they enter into the sensing data. Okay, and to what we eventually want to do, we want to, for example, do a stabilization of the drone, okay? The first case, so it's called regulation, or so again, you can think that the drone has to hover, okay? Okay, so let's see what we can do. So we have this switching logic that you see on the little purple thing over there on the left, which is actually also goes down to the green. And so we want to be very uncertain, and we want to have this probabilistic switching that balances between uncertainty and optimality, okay? So again, I want to make sure that I switch between sensors and actuators, that keep my system controllable and observable, but they will also guarantee a level of optimality, okay? And of course, the reactive, as I said, it's something that, let's say the attacker was lucky enough, found what we're using, and then we detect it as well. In order for us to do that, of course, you have to assume that you have redundancy, right? So I have a redundant set of actuators, a redundant set of sensors, okay? Of course, every time I have to make sure again that my system is controllable, means that I can move it, I can control my system to move it from point A to point B, and also observable, that I mean I can reconstruct my whole information by just measuring partial information, okay, from my sensors. Okay, so again, the idea of this one is pretty simple. We use, don't worry too much about the math too much about it. So we use a simple unpredictability measure, which is entropy-based, okay? And this actually balances between optimality and uncertainty. Again, we have a bunch of sensors or actuators, and eventually we switch between all of them to guarantee a form of controllability and observability, and this happens with a specific probability, okay? So, and this is based on this simple optimization that you see at the bottom of the page. Okay, so of course, every time we do something with a system, a drone, aircraft, or anything, I have to make sure as a control theorist that the system is stable, right? So it means I will not do something crazy, and I will eventually fulfill my mission. So we provide these guarantees. We find what is the switching that I have to switch between the sensor and actuators, how fast I have to switch for me to guarantee stability. So again, I want to stabilize my system, and while I do that, I don't want to lose this form of stability, okay? Again, don't worry too much about the math, but the idea is that everything that we have done here, I lost one, okay, is stable. Okay, so let's see actually now, let's say that the attacker was lucky enough and found what sensor and actuators we were using. So what we have done, we developed a model-free detection signal that can measure in real time how far we are from optimality, okay? Let's say that we want to use an optimal control framework that optimizes, let's say, fuel, time, or energy of the state and the control. And I want to see how far I am from optimality. So you see here some V's and some performances. So the V, you can think it's like a value function. I measure how far I am from optimality, and then if I'm far from optimality, I declare it as an attack on specific sensor actuator, okay? Again, we always, this is, if you're familiar with the Bellman equation, you can consider that this is a form of an integral Bellman error, okay? Of course, you know that Richard Bellman was the one who invented dynamic programming. And actually, there's a funny story about that, because his boss didn't like math research. So at Rand Corporation, he said, okay, I'm not doing really math research, I'm doing programming, so that's why he called it dynamic programming. And then he changed the world in optimal control learning and so on and so forth. Okay, so again, as I said, everything that we provide here is proven through theorems. Don't worry too much about it. But what I want you to see is that I can declare an attack if this error is not 0, and then I can also quantify my loss. Okay, so let's see actually how this can work together. So the proactive defense works always, and I also measure this error. Okay, so if this error is different than 0 at the active controller, so then I take it as an attack on the specific actuator. I take it out of the switching queue, which is the moving target defense, and I continue switching. Okay, so this is how reactive and proactive they work together. And again, we want, whenever you put everything together, to guarantee a form of stability. Okay, let's see how this can work. So there is a benchmark aircraft, which is the Admire, which actually was developed by Saab. So this, by definition, it has a redundancy of 7 in the actuation and 2 in the sensing, okay? So, so these are just some matrices, don't worry too much about it. Again, what I want you to see here in the next slide is that I will switch between controllable subset of actuators, and then I will utilize this physical sensor redundancy to provide tolerance to attacks. So, again, for those of you who are not familiar with aerospace, so the canard or elevon provide the pitch moment. For all, the elevons are the only active control surface, and the rudder is used for yaw, okay? So, what you see here on the upper left is switching between the different actuators, okay? And then since I'm using optimality, you see that my framework is using actuator number 4, mostly, right, okay? So this is the proactive. And again, you see that while I'm still switching, all my states, which is the angle of attack, is the side slip angle, they're all pitch and yaw, as well as the control signals, they're stable, okay? So again, this is only the proactive, the moving target defense, okay? So of course, if I have a smart attacker, the actuator that the attacker will attack will be number 4, right? So let's see what happens. Okay, so again, this is just some trade-off between optimality. Don't worry too much about this one. So let's say now that the attacker figure out that I'm using number 4, okay? And I don't have the detection mechanism, which is the reactive, okay? So of course, if I don't have that, you will see that my system will go crazy, and then my aircraft will go down, okay? So let's see what happens, though, when I detect it with my reactive, okay? So again, you see the switching in the blue lines is number 4. The attacker attacked number 4, okay? I take it out of the switching queue because I identified it, and then still my system is stable. So these are the states of the system together with the proactive and reactive, okay? Of course, I can do similar things when I have attacks on my sensors, and then here you see the detection of sensor attacks, which happens between the second 10th and 20th, and I'm still able to find and estimate my angle of attack, okay? Okay, so now I will talk about something that we integrate all this and then we transfer it to the industry, and also we transfer it to the Department of Defense. So this is a tool that it has human AI interaction for security. that integrates the reactive and proactive defense that you saw before, and develops a trust between humans and AI, and whoever you trust more takes over and predicts attacks and secures your system, okay? So it's actually a human-AI interaction. Whoever you trust, you take over. Again, this is everything that the tool that does. So you see here it says autonomous system under trust, human please return control to autonomous system. Here you see some states. Here the human can detect the attack and so on and so forth, okay? But again, you can, this interaction between AI and humans for security of any systems, we have tried it to this subsystem before. We have tried on drones, and this technology has been delivered to the Department of Defense. So this is also some cool examples of a little drone that here you see that I have been using a PID, okay? And then an LQR, you see the system is stable. And then what happens in a bit, I will use this model-free detection, and I will detect the attack, and I will still be able to guarantee that the system is still stable, okay? So you see this is how the attack detection happens in real time. I have a couple of minutes more. Okay, so of course, I also promised that I will talk about learning a little bit, although I had some learning parts in the beginning, but I will be very brief about it. So you will see that reinforcement learning is in between different cool topics like optimal control, operations research, game theory, and so on and so forth. And then we have been working on real-time reinforcement learning, which means that there is no pre-training. Okay, so your system learns on the fly without any pre-training. Okay, so I know that most of learning happens offline, and then you take your controllers that you have learned in some cases, and you put in your system. Here, everything happens in real time because we have the beauty of feedback. Okay, so these are just different things. For example, you can call it automatic, adaptive, autonomous. So autonomous is the time that you have cognition, okay? So I know nowadays different people claim autonomy on this spectrum, on all this spectrum, but I think the time that you have cognition, then and only then you can claim autonomy, okay? Again, we have done reinforcement learning in case of pursuit evasion with drones. So here you see that we have a target, and then we want eventually our drones to collaborate to monitor the target, okay? And everything happens in a model-free scenario. We have done it also in the 3D space, where here you can see 3 aircrafts. So you have 2 pursuers, 1 evader, but you want to make sure that at least 1 pursuer has its camera on the evader, okay? So this is a project we have done for geofencing and so on and so forth. Again, this is just some plots. We have done also control with very sparse rewards, and we have applied that to several motion planning strategies. So what you see in these small videos is you can see some drones that, again, everything happens in real time. So you see as they move, they discover new obstacles, and then they reroute in real time their strategies, okay? So, and nothing here is pre-computed. The controller is computed in real time, and it doesn't require information about the physics of the system. Again, my last slides are what we have been using at Georgia Tech. So we have these little crazy flies, I'm sure most of you are familiar with. So we have used it as isolated drones as well as swarm operation. These are our facilities. So we have very big indoor facilities. And then we have around about 20 cameras. And we run very cool experiments there. We also have a fund to create some wingcasts. Also, we have another room where we have a projector on the ground where we can develop virtual obstacles and navigate our drones over there. So again, this is our little Crazy Fly, which you can have you can use Crazy Fly's controller, which actually are, I think they have a Pix4 controller as well. You can use the PIDs, but actually we have programmed it ourselves, and we have done some learning stuff on them. Again, positioning here can be done in different ways. So it can be with a marker deck where you can mark it through the cameras. Okay, you can use it as a flow deck where you have a camera below, and then this navigates, but it has to find a pattern. And then you have an AI deck that you can run different things. Again, this is how the motion capture capabilities work. Of course, the little dots that you see on top, the gray dots, they have to have a unique configuration if you have multiple drones, so you can identify and guarantee where your drone is at every time. Again, as I said, we have been working on these model-free controllers, where it sounds like a movie because you have a critic where it tells you how good your controller is, and you have an actor where it implements your control policy. So finally, we have some movie, but I don't have enough time to show it. Let me see. So again, we have run this in, I will say, oh, you can barely see it. I know I don't have enough time, but let's say we have a drone that in real time learns how to navigate and can do that even in the presence of sparse rewards. And then with that, I'll be happy to talk to you offline about different things. I know we don't have enough time, but you can find my information in my webpage, or you can send me an email, and I will be happy to talk to you more about that, as well as we have faculty positions at Georgia Tech in my department. I'm leading the controls part, so if you have any interest, come talk to me. I'll be happy to tell you anything, okay? Thank you very much.